right? This is your minus omega A, right? So if you look at the function, it's linear. The y-intercept is 0. So this is your 0 to A. Okay. And then A to L is a constant minus omega A. Okay. So minus omega A is just a straight line. Okay. And then the reaction at point C, okay, will be upwards, and it's going to push it back this way. Right. So this is your shear force diagram. Okay. Next, we're going to draw our bending moment diagram. And by looking at how the structure is loaded, I'm only going to concentrate on negative bending. Okay. And I'll tell you why later on. Okay. So if you next, this is your X. Right. So this is your X. And then, as I said, I'm going to only focus on negative bending. M. Now, why are we focusing on negative bending? Okay, and now I think I said this in the lecture, but I'll repeat again. So if you look at the deformation pattern, right? When your moment is positive, the deformation will be like this. Smiling face sort of deformation. Okay. So, but when your moment is negative, your deformation pattern will look like this. Now, this is deformation pattern, not the bending moment equation. Okay, right. So when you look at the moment equation again, okay, so again we're going to start from 0, and over here, this is our point A. Our distance A over here is your distance L. So if you look at that over here, so the function is minus omega x squared over 2. Okay, so it's going to be a set phase. Okay, and then it's going to stop at minus what? It's going to stop at minus omega a squared over 2. Okay, so you have set phase. Okay, and then from here, what you observe based on the moment is you are going to see a a moment that is minus omega ax plus by omega a squared over 2. Okay, so when at a distance L, okay, so at a distance L over here, right, you will see a straight line like this because it's a straight line function, right? So from here to here, you see a straight line. And this value over here is equal to minus omega a L plus by omega a squared over 2. Okay. I think I overshot slightly, my bad. It should be somewhere around here. So one thing to observe is this. Okay, what's the relationship between shear force and bending moment diagram? Okay, so if we are to look at 0 to A, so I'm going to partition this. I'm going to corner this up. Okay, so if you look at 0 to A, right, your shear force is negative. Hey, sorry. Your shear force, you have negative magnitude, right? Over here, you have negative gradient. Right? What do I mean by negative? If you draw a tangent, the gradient is what? Negative. Again, from A to L, negative magnitude, and this is also negative what? Gradient. So if positive shear force, you will have what? Positive magnitude, but we did not observe this. Okay. So what you see over here, right? Okay, as you can be observed over here, where the structure will fail, the structure will fail at here because bending moment is the what? It is the maximum. Yes or no? All right. So if you look at the bending moment, it's at maximum. So at point C is where failure will occur. Okay. Now, some of you might say, Eugene, can we do from right to left? You can. Okay. The thing is now, if you want to do from right to left, okay, if let's say I'm going to do from right to left, okay, I'm just going to do a point. So let's say now you're going to look at this from right to left, right? So the only dilemma is this. If you're going to do from right to left, right? So this is point A, point B, and point C, right? If now we want to do our analysis from right to left, you need to find the reaction from right to left or at point C. Okay, so right to left, okay, you need to find. So we need to find what's the reaction. So we know that over here, right? This is our omega A. So what am I trying to do down here? We want to find the reaction at point C, okay, to analyze the structure from right to left. Okay, so now we have to find the reaction at point C. So we know that this is omega A, right? And then we will know that this over here will be your CY. Okay, let me draw a transformation. So this is X, Y, this is rotation about Z. And then we have a counter moment over here. This is moment at point C. Okay, that's our moment at point C, right? So we are going to do our we're going to do our moment equation. Okay, or not moment, we're going to do static analysis. Right, so before we do our static analysis, let's get our distance right. So from here to here is A/2. The distance from here to here is L minus A/2, right? So we are going to do summation of forces in the y direction to find Cy. So you have minus omega A, right, plus by Cy is equal to 0. So Cy is equal to omega A. Okay, so you do see that in our diagram also, because our diagram, when we finish off our diagram, the structure is in this configuration, right? So remember, when I draw the vertical line up, okay, when we draw when we draw the vertical line up, when it's going up this way, it's going up is because it's what? Positive omega A. Okay, that's why you have positive over here, in case you are confused. Okay, so this is your Cy, and then your moment about point C. So we're going to take summation about moment, okay, Z at point C. So we're going to take our moment at point C, right? So we will have so this one will be going anti-clockwise, so it's omega A, all right, L minus by A/2, all right, and then this one will be minus M at point C. So M at point C is equal to omega AL minus by omega A squared over 2. Okay, so you'll ask yourself, why is this opposite, Eugene? You'll say, Eugene, why is this opposite? Because this is the what? Reaction of the wall. Okay, so the wall is in the built-in wall is doing a counter reaction. So you will realize that the magnitude is exactly the same, but the direction changes. Okay, so in this context, that's why in a cantilever beam, right, the structure is not rotating. In a simply supported, it is rotating. Okay, so now is the same. Okay, by looking whether you analyze left to right or right to left. Okay, so I'll do a very short one if we analyze from right to left. Okay, so now we know our reaction. Okay, I was going to do this example, but I will do this maybe in the lecture. So now, we are going to do from point B, not point B, but we're going to do from A, X to L, okay? And this is from point B to point C, okay? So point B to point C, right? Our geometric datum is still the same, all right? So this is X, the distance from here to here. Now this is what? L minus what? X, right? So we know that we have a moment. With our moment is equal to omega AL minus omega A squared. Okay, so we have a moment over here. Omega AL minus by omega, wait, I have very bad short-term memory, minus omega A squared over 2. Right? And then we have a reaction down here. The reaction down there is equal to what? Omega A. Okay, omega A. Then we assume what? Positive shear. So V as a function of X, moment as a function of X. Okay. So static analysis. So I mentioned about forces in the Y direction is equal to 0. Right. So you have omega A, right, plus by V as a function of X is equal to 0. So V as a function of X is equal to minus omega A. Exactly the same, right? Now we're going to take moment over here, right? We're going to take the moment at that point over here. So I mentioned about moment in the Z direction anywhere at point X. Okay, point X is where this dot is, right? It's our variable. So we have a moment. So moment, we have a moment that is going in a clockwise. So omega A L. Sorry, this was minus. I beg your pardon. Minus by minus by omega AL minus by omega A squared divided by 2. Okay, let me write this out properly. Sorry. Omega AL minus by omega A squared over 2. Right? And mx is also going clockwise, so minus m as a function of x is equal to 0. So m as a function of x now is equal to is equal to, so I brought this, so equal to minus omega AL. Okay, wait, I'm skipping to yeah, it's the same. So minus by omega AL minus by omega. Oh, sorry, I have something missing. I beg your pardon. My bad. Okay, I have something missing. I'm missing a term down here. I do apologize. So we will have our minus, clockwise is minus omega AL minus by omega A squared divided by 2, right? Then we have a plus omega A, right? L minus X. I miss out that one, okay? And then we have a minus m as a function of x. The whole thing is equal to 0. So now let me check. Clockwise, yep. Going anti-clockwise omega A, yep. So m as a function of x now will be equal to minus omega AL minus omega A squared over 2 plus by omega AL minus by omega AX, right? So we realize that when we remove the bracket, this and this can be cancelled. So it's equal to minus omega AX plus by omega A squared over 2. So you realize that these two functions, omega AX plus by omega A squared over 2, when we do from left to right, the function is also the same. Okay. So the advantage of doing from left to right is you no need to find the what? To find the reaction. When you do right to left, okay, like when we're trying to do right to left now, you have to find the reaction at point C. Okay. So there are times that you have to do left to right. There are times that you have to do like right to left. Okay. Any questions, please? Is this clear to all of you? Okay.
Yes,
And
just a quick question.
yes.
Is the bending moment the integral of shear force?
It is.
It is, right?
Yeah,
Okay.
it is. Okay, but I did not do that yet. Okay, this is a simpler method. Okay, you can also do that mathematically. You integrate your shear force equation, you get your bending moment. You get your bending moment equation. But you have to know your boundary condition. If you don't know your boundary condition, you're done. Okay, boundary condition. So in this case, you don't need to know your boundary condition. If you use the integration method, you need to know your what? Boundary condition. Okay. Any questions before I let you go? Anyone, please? No? If that's the case, I'm going to end my lecture here. Now, I've uploaded the homework, okay? So you can more or less do the homework already, okay? If that's the case, I'll see you guys on Tuesday, okay? Have a great weekend. Thank you. Bye.
Thank you.
Bye. Anyone have question, you can ask me, okay? If you have.